Hi everyone. So today we're going to be talking about taking the conic sections that we've been discussing all week, so ellipses, hyperbolas, and parabolas, and now we're going to be looking at taking them and shifting them left or right or up or down. So another thing that we're going to be kind of focusing on in this section is being able to tell the difference between what type of conic section you're given. So far we've, in each video, it's been like, okay, now we're going to graph ellipses. Now we're going to graph hyperbolas. Now we're going to graph parabolas. So today it's going to be a little bit more like, here's an equation. You have to figure out, what kind of a shape is that and use that to figure out how to graph it. So with that in mind, I just want to kind of summarize before we get into shifting them, what the kind of like unshifted conic sections, what their different equations look like, just so we have them all kind of summarized in one place. So this is kind of like a review from earlier in the week. So these are going to be the equations for unshifted conic sections. So when I say unshifted, that basically means that they either have their center at the origin, or for the case of a parabola, the vertex is at the origin. So one type that the first type that we looked at this week was, sorry, that's not right, ellipses. So an ellipse is of the form x squared over a squared plus y squared over b squared is equal to 1. So what about a hyperbola? What makes a hyperbola different? Well, for a hyperbola, instead of adding, you're subtracting. So it will either be x squared over a squared minus y squared over b squared is equal to 1, or, oops, I wrote that wrong, or starting with y squared over b squared minus x squared over a squared is equal to 1. So how can you tell if something is an ellipse versus a hyperbola? Basically, whether you're adding or subtracting. So last one that we talked about was the parabola. And so those ones, the equation either looked like y is equal to ax squared, or x is equal to ay squared. So how can you tell the difference between a parabola and these other ones? Well, notice that with the parabola, only one variable is being squared. And that's kind of the key difference, because even for like an ellipse and a hyperbola, sometimes they might not look exactly the way that they're written here. Maybe they won't have, I forgot a squared here. Like, just to give a quick example, you could be given an equation for an ellipse where it was like x squared, I'm kind of winging this, so hopefully this goes okay. Let's say it was like 4x squared plus 9y squared is equal to 36. So that doesn't look exactly like what we had for the ellipse, but if you were to go through and divide everything by 36, then it would, right? If you divided everything by 36, then you would get x squared over 9 plus y squared over 4 is equal to 1, and that you would know how to graph. So I just want to kind of point out that in this class, we're going to be working with conic sections that are written already in their standard form, but in the future, in another class, you might see them so they're not already written in standard form. But the key difference I really want to point out here is that even when it's not written in standard form, notice that the ellipse still has an x squared and a y squared, and it's being added. Versus if you had a hyperbola, even if it wasn't in standard form, there would be subtraction, and you would have both an x and a y squared. Versus for a parabola, regardless of what form it's in, it's only going to have one of the two variables squared. So that's kind of I'd say like the main important difference to recognize between, or differences to recognize between these different conic sections. Okay, so to get into shifting conic sections, I want to start with an example that you probably are already familiar with, or hopefully you remember from 141. So shifting conic sections. So I want to start with an example, and this is going to be an example of a circle, which technically is a type of ellipse, right? It's just an ellipse that hasn't been stretched horizontally or vertically. So my question is, how does the graph of x minus 2 squared plus y plus 3 squared equal 1 compared to just x squared plus y squared is equal to 1. So if you remember stuff from 141, you remember that you can figure out the center of a circle by looking at the numbers that are being subtracted from x and y. So because here we're subtracting a 2 and here we're subtracting -3, right? If you have a plus, that means it's minus -3. That would tell us that this one has a center of 2, -3. Whereas this one has a center of 0, 0. So let me just quickly sketch these two circles. So this one looks like this. And then the shifted one has a center of, we just said 2, -3. So that's here. So that looks like this. So to answer the question, how do these actually compare to each other? We can see that it has been shifted to the right by 2 and down by 3. So why is that? I want to just, before we kind of establish like the general rule, because they're basically all going to work like this, like that you can just kind of look and see what's being added or subtracted and use that to determine what the shift is. But I want to dig into like, why is that the case? So the way I want to think about that is by kind of comparing these two equations side by side. So I'm going to rewrite them in this other color. So if you have x squared plus y squared is equal to 1 versus the other one, x minus 2 squared plus y plus 3 squared is equal to 1. So the way I want to think about this is thinking about a point that lies on each of these graphs. So what's an example of an easy point that lies on the graph of this circle? Let's go with the point 1, 0. So the point 1, 0 lies on this graph, right? Because we can see that by just looking at the graph, but also because if you plug in 1 for x and 0 for y, you get 1 plus 0 is equal to 1. So what would be like a corresponding point that would lie on the graph of this green one? Well, let's think about what would you need to put here in order to make it be equal to 1? Because, right, like the reason that, and maybe let me even write this, I'm going to write this out in a little more detail. So I'm going to say this contains the point 1, 0 because 1 squared plus 0 squared is equal to 1. So what I want to think about is what would we need to plug in into this first parenthesis? What would we need to plug into for x in order to get 1? So if we were to plug in 3, so I'll write that down here. So if we were to plug in 3 for x, we would get 3 minus 2, which is the same as 1 squared. And then what would we need to plug in for y? Well, if we plug in -3 for y, that will give us 0. So that would be 1 squared plus 0 squared is equal to 1. So this contains the point So what numbers did we actually plug in for x? We plugged in 3 and -3. So this contains the point 3, -3, because basically when we plug it in, we get a true statement. So where is that like shift coming from? It's basically coming from the fact that in order to achieve the same kind of result that we had at the point 1, 0, we had to plug in, instead of plugging in 1 for x, we had to plug in 3 for x because we are subtracting 2 from it, right? Whatever we're plugging in for x, we're then subtracting 2 from that number. And so in order to kind of get the same corresponding result to what we got in the first circle, we need to plug in a 3 for x. And then if we want to get a 0 for this second part of the equation, the way that we did here, well, then we would need to plug in, instead of 0 for y, we would need to plug in -3 for y. And so if you compare these 2 points, the point 1, 0 and the point 3, negative 3, which you can see are kind of like corresponding points in the graph, we can see that between those 2 points, we've been shifting to the right by 2, and then we shifted down by 3. So, I guess bottom line is that the reason that adding or subtracting numbers to x and y give you a shift is because they're basically forcing you to plug in different numbers to get the same result that you did with the kind of like basic form of the equation. So that same rule is going to apply actually in all of our conic sections, and actually in graphs in general. I'm going to write it down as a rule just for conic sections since that's like what we're talking about right now, but it is going to be generally true for other graphs as well. So in general, for any conic section, so we're going to have a few different rules here. So replacing x with x minus n shifts the graph right by n units. So it kind of goes, this is something we're familiar with from pre-calculus, from pre-calculus 1. It goes kind of the opposite direction than you would think. So subtracting shifts it to the right, and then replacing x with x plus n shifts the graph to the left by n. And so if you want to understand why is it that it goes like the opposite direction, I would really just kind of go back to this example. And I think this is one of those things that you might need to sit down and kind of convince yourself. Pick another point on this graph, maybe the point 0, 1, and try to kind of do the same thing. And you'll basically see that like, because we're subtracting 2 from x, in order to get the same results that we got in the first function, we're forced to plug in numbers that are 2 bigger than x. Because we're subtracting 2, it's this kind of idea of compensating. To compensate for that subtracting of 2, we need to plug in a number that is 2 bigger. And so that means it's going to the right by 2. And because of that idea, it's going to be the exact same deal for y. So I know that from pre-calculus, maybe you're used to the fact that x and y kind of work differently. But the reason that it was different in pre-calculus is because in pre-calculus we were dealing with functions where you would have y on one side and everything else on the other side. But now we're dealing with conic sections where the x's and y's can be on the same side of the equation. And really, you can see directly that you're adding and subtracting things to y itself and not to like the function as a whole in the same way. But I think that last sentence was a little confusing, but yeah, we'll see when we get into some examples. I think that will help as well. But yeah, bottom line is that x and y are going to basically act the same way. So replacing y with y minus n is going to shift the graph up by n. And then replacing y with y plus n shifts the graph down by n. So both x and y are being treated kind of equally in this case, and they're both, whatever you're adding or subtracting, you're kind of doing the opposite direction as what you might initially expect. Okay. So basically the rest of this video, we're just going to do some different examples of graphing different conic sections. And, I'm not going to say, oh, let's graph this ellipse or let's graph this hyperbola. That's going to be part of the point, is to figure out, what is the conic section that we're graphing, and then kind of make sense of the equation and the shift and kind of put all that information together. So the first example I want to do here is, I don't know why I moved that down. So let's graph the conic section that is given by y minus 1 squared over, and let me make sure I actually changed this example. Okay, yeah. I change this example from what was on my notes, and I just wanted to make sure I was doing it right. Okay, so what's going on here? So first thing we need to decide is whether this is a hyperbola, a parabola, or an ellipse. So how can we tell that this is, what shape this is? We want to look at, first of all, are both x and y being squared? If so, that means it's a hyperbola or an ellipse. And then also at, is it plus or minus? So we have both x and y being squared, and we have a minus here, and so that tells us that this is a hyperbola. So this is a hyperbola. So there's a few things that we can kind of gather from this equation, and some of it is stuff that we talked about in a previous video, and then some of it is new. So I'm going to rewrite this as, you'll see, as basically rewriting the denominators as something squared, because that's what we have been doing in the past to really see what the shape of our graph is going to look like. So I'm going to rewrite this as 4 squared and 3 squared. So that's going to tell us basically this, remember with hyperbolas, you kind of draw this rectangle. That's like your kind of like a guidance for what the shape of the hyperbola is going to look like. But then additionally, we need to figure out where this whole thing is kind of centered. So if it was just x squared and y squared, we would draw that rectangle centered at 0, 0. But in this case, we can see that this has been shifted to the, or this, so first we're looking at y, so this is going up by 1. And then here we see that we're adding 3 to x, so that's going to go left by 3. So when we go to draw this, we're going to do almost the exact same approach we did in the other video about hyperbolas, but we're going to start by kind of centering ourselves. So we're supposed to, we see that we've shifted left 3 and up 1, so that's going to kind of put the center of our box here. And so it's almost like you're pretending like that point is the origin when you're going to draw this hyperbola. So from here, we can use the values that are paired with x and y. So we see that the value that is paired with x is 3. And so that means that our rectangle we're going to draw is going to go to the right by 3. And then we can see that the value that's paired with y is 4 squared. And so that tells us that our rectangle is going to go up by 4. And so then we can draw the rest of the rectangle. So it also is going to go to the left by 3, and it's also going to go down by 4. So that's going to give us a rectangle that looks like this. So maybe I'll even draw here. So this is also 3. This is also 4. Okay, so once we have this rectangle drawn, then we can draw our asymptotes. So the asymptotes are going to be what you get by just drawing a diagonal line that goes through the box and then kind of continue them in the same direction that they were initially. And so here, same thing. So we have a diagonal line coming through here. Okay, and then the last decision we have to make is where does this graph go? So because the y part comes first, that tells us that the graph is going to be on the top and the bottom. So we kind of just go to the middle of the top and the bottom and put a point there. And then you just want to draw these two kind of curving pieces, which eventually get closer and closer to the asymptotes that we drew. So I mentioned this like basically every time we've drawn these, but I just really want to make it clear that, I know this picture looks kind of crazy. It looks like there's a lot going on. The only part of this graph that is the actual graph of the hyperbola is the part that I graphed in black. Everything else is there to kind of help us draw it, but the actual graph of the hyperbola is only the part in black. So I just want to make sure that everyone's aware of that. Okay, so let's do another one. So next we're going to graph let's do x plus 1 over 4, or x plus 1 squared over 4, plus y minus 2 squared over 9 is equal to 1. So first thing we want to decide is what kind of a shape this is. So because both x and y they're both being squared, that tells us that it is either a hyperbola or an ellipse. And then we see that we have a plus sign here, so that means it's an ellipse. So we can start by rewriting this as x plus 1 squared over 2 squared plus y minus 2 squared over 3 squared is equal to 1. And then we want to think about the shift that's going on here. So we added 1 to x, and so that means it's going to go left by 1. And then we subtracted 2 from y, and so that means it's going to go up by 2. So that means that before we even start kind of drawing this, we want to think about like where is the center, and we want to move that somewhere else. So the center of this thing is going to be to the left 1 and up by 2, so it's going to be like here. And one thing I mentioned in yesterday's video, I think, or maybe not yesterday, but like 2 days ago, is that really the process for drawing an ellipse and a hyperbola is actually really similar. It's just that when you draw the ellipse, you're kind of on the inside of that box, and when you're drawing the hyperbola, you're on the outside. So you don't have to draw a box for the ellipse, because really like the main purpose of drawing this box is to get the asymptotes, and you don't need that for the ellipse. But just to say this again, because I think I mentioned it the other day, but let's say that this had been plus instead. What would that ellipse look like? It would just be the ellipse that goes right inside of this box, right? Because the numbers that we used in order to draw the box were exactly the same numbers you would use to figure out how far horizontally and vertically to stretch the ellipse. So that's what I mean when I say that, you know, it's basically the same, drawing the hyperbola and the ellipse up until the part where you actually, you know, draw the shape. Okay, so this tells us that we want to horizontally go 2 in each direction, right? So we need to have like, it's not really a radius because it's different in each direction, but it's kind of like a radius. So our horizontal quote unquote radius is 2, and then our vertical quote unquote radius is 3. And so our actual ellipse is just going to be the oval shape that has those as its kind of support outline structuring. Okay, couple more examples. So next one I want to do is a graph. Let's do y is equal to x minus 3 squared plus 1. So this is not written really in the same form as some of the other ones, and I did that on purpose because I want to kind of show you how the way that you've probably learned how to graph parabolas, how it is actually still consistent with what we talked about here. So let me go back to that. So why is this not quite in the same form as the other ones? Well, the plus 1 is just kind of floating by itself. If we instead were to subtract it from y, then this would look a little bit more like the other ones in the sense that the numbers that are being added or subtracted are kind of directly with the variable. There's no number just kind of floating around on its own. So forgetting for a second about the way that I just rewrote it, let's say that you were just given this equation and you were asked to graph it. So what you'd probably think is like, okay, well, this means that I go left by 3. No, let me do it in the same, or sorry, not left, right by 3 because we're subtracting. And then if you remember going back to transformations with functions, if you're adding 1 kind of outside the function, then that means you're going up by 1. So if we instead move that 1 over so that it's with the y, that still works, right? Like just to give another example, right here, we had y minus 1 squared, and we saw that minus 1 and we're like, okay, that means up 1. So that's what I meant earlier when I said that, you know, the way we were doing it before when we had that number on the other side, that forced us to kind of see x and y as having a different kind of shift going on. Whereas if we put it on the same side, then it's the same. So subtracting goes in the positive direction, adding goes in the negative direction. So it doesn't really matter which way you write it, but I just wanted to kind of show you both ways. So in either case, you would interpret these as being up 1 and right by 3. So this is going to be a parabola that has no stretch, right? There's no number out front. So it's just kind of a standard parabola that's been moved to the right 3 and up by 1. So its vertex is going to be at the point 3, 1. And then you can graph a few more points. Like I said, I really like just kind of knowing the shape that you go over 1, up 1, over 1, up 3, over 1, up 3. And then you can connect these. And I did not do a great job there. Do that a little better. And that would be our parabola. Okay, let's do one more. So this one we're going to graph x minus 2 is equal to y plus 1 squared. So this one is given to you in the format where we can just kind of go right into the same kind of I don't want to say transformations, but the same kind of shifts that we were working with the other conic sections, right? So we can just say, okay, we're subtracting 2 from x. That means that we're going to the right by 2. And we're adding 1 to y. That means that we're going to the left, or sorry, not left, down, right? Because plus is going to make it go down by 1. So we can draw this. So what is this going to look like? Generally speaking, it's going to be a sideways parabola, right? Because it's y that's getting squared rather than x that's getting squared. And so the vertex is going to be right 2, down 1. So it's going to be here. And then there's no stretch there. You know, if there's a number here like 3 or 2 or something, then we would have to draw the shape differently. But because there isn't, we can just do that same shape that we did in the last one. So it's going to look something like this. All right, so that is it for today.